Hello and welcome everybody to this webcast. Now is the time to get started. Today you will watch the presentation about knee contact force estimation using force reaction elements. And this research was declared as the winner of the 6th Knee Grand Challenge competition. My name is Moon Gi-jung, who is working as Senior Application Engineer at AnyBody Technology, and I will be the host of this webcast. And Professor Seung-bum Gu, who is an Associate Professor of Jungwon University in South Korea, will be the presenter. Also, there is Iwan Jung, who is a PhD candidate of Jungwon University, will be the main panelist. He is also one of the main contributors of this research. On the left-hand side, you will see the schedule of this webcast. First, I will briefly introduce what AnyBody modeling system is. Next, the presenter will explain what Grand Knee Challenge competition to predict in VIVO knee load is. After that, you can see how the custom knee contact model in this research was implemented using AnyBody modeling system. And also, you will see the prediction result and the discussion from this research. Finally, we will have the session for questions and answers. This slide is for those of you who haven't used this webinar system before. On the right side of your screen, you will see a control panel. It can be collapsed and expanded by pushing the red button. If you think of a question during the presentation, then please don't hold back and don't wait until the webinar is over. Just open the control panel and find the questions panel. There you can write questions immediately. We will try to answer as many questions as possible at the end of this presentation. Some of our panelist members may also answer your questions directly, or if your question is not addressed, we will try to do so by emails. Now, there will be a short introduction of AnyBody for those who are new to this technology. Then, what is AnyBody exactly? We usually divide it into software and model. For software, AnyBody modeling system, its abbreviation is usually there for AMS. This is the software which runs simulations of a human musculoskeletal system. And with this software, there is AnyBody managed model repository, that is what we call AMMR. This contains various models including our full body human model, and there is the library of various applications. Here you see a screenshot of the full body model in the middle, and surrounding you see some details of the model. The model is the most detailed musculoskeletal model to be found. It contains more than almost 1,000 individual muscle units. It's a generic model, parameterized in many ways. It's an open model that is validated and fully scalable. Open model means that it is open to be adapted to your particular needs. Everything in the model is accessible and documented with publications. So if you want to change muscles, bones, or joints, you can easily do that. Fully scalable means also that you can change the model from a typical European male to almost whatever you want the model to be like. Also, AnyBody supports a patient-specific scaling feature using bone geometry. Details can be found in our previous webcast. This slide explains the principle of AnyBody briefly. AnyBody does an inverse dynamics simulation, which means that it requires motion and external forces as input in general. Of course, now AnyBody users have an option to predict the ground reaction forces as well. Using the muscle recruitment optimization solver with various options of objective functions, then AnyBody calculates all the internal musculoskeletal values such as muscle forces, muscle activations, joint reaction forces, and so on. Here we see the wide range of applications, and these are the typical domains that AnyBody modeling system can be applied to. Today, I'm very happy to have Dr. Seung-Bum Gu here. Between 2002 and 2007, he had been a PhD and a postdoctoral fellow in the Department of Mechanical Engineering at Stanford University. After that, between 2007 and 2009, he was a research scientific staff in radiology at Stanford University. And since 2009, he has been an assistant and an associate professor at Jungwon University in South Korea. Now I will make him as the presenter in our GoToMeeting system. Then from now, everyone will see his screen. Just a moment, please.
Hello everyone. I'm Seung-Bum Gu in Jungwon University. We thank for the webcast invitation from AnyBody Technology and all audiences in this session. We recently won in the 6th Grand Challenge competition to predict in vivo knee load using a full body model in AnyBody modeling system. Organizers of the competition really put great effort. We again thank the organizers of the competition. 6 teams joined the 6th competition. It was a manuscript-based competition this time. Some of the works were published in Journal of Biomechanical Engineering early this year. Our work is also published in Journal of Biomechanical Engineering. This presentation is based on our work described in this paper. The competition provided a great chance to validate performance of musculoskeletal model and simulation, and to understand the factors affecting simulation accuracy. It would eventually help understand pathomechanics of musculoskeletal disease and develop its treatment. In the competition, organizers provided a set of measured data of subject with electronic total knee arthroplasty. The data included motion capture data, ground reaction force, EMG signals of lower limb muscles, radiograph, and CT images. Competition participants made dynamics models and ran simulations to predict medial and lateral contact forces in the knee. In the first round of the competition, almost all externally measurable data were provided, but the measured in vivo knee loads were not provided. The predicted knee contact forces were submitted to the competition organizers. In the second round, the measured in vivo knee loads were released. Participants were asked to improve their model and simulation. Updated knee contact forces were submitted along with a manuscript. Organizers evaluated not only the accuracy of predictions, but also novelty of modeling method, lessons learned from unblinded predictions, and quality and completeness of manuscript. In previous years of the competition, a few teams used forward dynamics-based optimization methods that utilize deformable contact models. These methods required model parameters to be determined heuristically or from preliminary tests of subject. A few other teams used inverse dynamics-based optimization methods with detailed knee models including ligaments. The non-subject specific and relatively large strengths of the knee ligament seem to have had a large influence on contact force calculation. The objectives of our study were to develop a simpler knee contact model without ligament, and to investigate the effect of limb alignment and joint type of the knee on knee load estimation. In the sixth competition, a male subject with height 172 cm and weight 70 kg was tested for smooth gait and bounce gait. There are various externally measured data. We used motion capture data, ground reaction force, CT image, and frontal long leg radiograph. In our previous study, we developed a method to predict full ground reaction force using multiple reaction elements between the foot and ground. We could validate accuracy of the method using force plate data. We used the same idea in the knee with the assumption that knee contact force dominates the internal forces in the knee. We installed 32 reaction elements on the surface of the tibial insert. They were divided into medial and lateral groups. Each reaction element contained push and pull component in 3 orthogonal directions, resulting in 6 force components. Locations of the reaction element were the point of force application from the perspective of the femur, and each force could act in any three-dimensional direction. Force component in reaction element worked as muscles. We used any general muscle class in AnyBody modeling system to implement the reaction element. Forces of body muscles and force component in the reaction element were determined simultaneously in the optimization to minimize the sum of cubes of activation levels subject to force and moment equilibrium conditions. We added a little bit of our skills in the full body model to predict anatomical landmarks on bone surface. Previously, we developed a method to predict attachment site of muscles and ligament on bone surface using local bone shape matching. In this method, a rectangular division map is mapped to bone surfaces through a spherical mapping to identify anatomical regions. The regions on the reference model and target models are matched separately to transfer anatomical landmarks on the reference model to the target model. Polygonal models of the femur and tibia were extracted from the subject CT image. The original anatomical landmarks on the AnyBody full body model were transferred to the subject polygonal model using our mapping method. We replaced the femur and tibia of the full body model in AnyBody with the subject bone models along with anatomical landmarks. Locations of 7 leg markers were perturbed by 3 cm. One marker was moved to one direction per perturbation trial. Therefore, there were total 43 perturbation trials for each gait trial. We did this to understand the robustness and variation of knee contact force estimation in case that there exist marker location errors. Mean and one standard deviation of knee contact forces were determined. Here we have the contact force estimation result. The black line represents measured medial contact force when the subject performed smooth gait. The blue line is the estimated medial contact force using the nominal marker locations. The red lines represent the range of variation of the contact force when markers were perturbed. Here are lateral and total contact force estimation for smooth gait. They were repeated for the bounce gait trial. Root mean scale errors of the predicted medial and lateral contact forces of the smooth gait trial were around 150 newtons and 300 newtons, respectively. We developed a simple knee contact model without knee ligament. Tensions in ACL and PCL are relatively low during walking in a previous study. Therefore, articular contact forces would dominate the internal forces in the knee during walking. Contact forces were calculated from the three-dimensional forces received by densely and equally distributed contact element on contact surfaces. Computation time was relatively short in this inverse dynamics-based optimization in AnyBody modeling system, compared with the time in forward dynamics-based optimization method. When the measured data were announced for the second round, estimation for medial contact force looked good compared with previous studies. Estimation error for lateral contact force was relatively large. When we looked at the measured data carefully, the measured data of the subject showed the phenomenon typically observed in patients with valgus deformity. The lateral contact force was as high as the medial contact force. In the model for blinded test, we used the hinge joint and did not take the lower limb alignment of the subject into account. Valgus deformity in the subject may have affected the joint kinetics calculation. We made modifications in the model in the second round based on our observation of the error. In our initial model, the hinge joint in the knee was not well aligned with the rotation axis of the subject knee. In the second model, we replaced the hinge joint with the ball and socket joint to capture the abnormal kinematics of the subject's lower limb. Also, the marker positions in the leg were adjusted to align the lower limb with the frontal leg, long leg radiograph during a standing trial provided in the competition. Here are our AnyBody simulations for smooth gait and bounce gait. You can see gray balls in the middle of the knee, representing the locations of reaction element. The black lines represent vertical and horizontal forces in each reaction element. The contact force prediction was repeated with the modified model. In the smooth gait simulation, the medial force prediction was a little bit improved. Still, the bump in the mid stance could not be captured in the simulation. Lateral force prediction was much improved. We could closely capture the first and second peaks. In the bouncy gait simulation, the prediction showed the similar pattern as in smooth gait. Average root mean scale error were decreased to 144 newtons and 179 newtons for the medial and lateral contact forces, respectively. The reduction of RMSE errors compared with the initial model were 15% and 61% for the medial and lateral contact forces, respectively. We further looked into the effect of joint type change and limb alignment change separately. Both changes improved lateral contact force estimation. Adjustment of limb alignment improved the estimation of the second peak in medial contact force. The two changes together produced greater improvement than either change separately, as shown in previous slide. The prediction accuracy was improved by using a ball and socket joint and anatomical lower limb alignment. Use of a ball and socket joint in the knee model allows the knee to rotate around the correct functional axis. Our model needs further improvement to predict knee load during not only walking but also various activities by implementing the roll of ligament. In summary, knee contact force could be estimated with a simple knee model with reaction element on contact surface during walking when knee ligament tension is low. Abnormal knee alignment should be taken care of with ball and socket joint and anatomical marker positions if anatomical images such as lower limb radiograph is available. In my lab, some students studied joint skeletal kinematics in the knee, foot, and ankle using a custom biplane fluoroscopy system. We do study musculoskeletal simulation of the knee, foot, and ankle. We developed geometric algorithm to identify skeletal geometry. These two students contributed to this study. Iwan Jung was the first author of this study, and he is here to answer your questions on technical aspect of the study. We would like to thank all listeners and funding sources. Thank you.
Thank you very much for your nice presentation, Professor Seung-Bum Gu. Now I will suggest a few closing remarks before we move on to the actual question and answer session. So this is a good time for you to write your questions on the question panel. The next AnyBody webcast will be scheduled on the 12th of May, and its title is Investigation of Muscle Activation During Active Sitting. You can see its picture on the right-hand side. More detailed descriptions are available on our website, so please check it afterwards. Also, you can see many of our previous webcast recordings on our official YouTube channel. You can find it by searching AnyBody Technology on YouTube website. On our official website, you can check out future events, and also you can see the updated list of publications that you might be interested in. In our AnyScript website, you will see our wiki pages and forum where you can find a lot of useful supplementary information. If you want to ask any inquiries about software, license, or technology, then please don't hesitate to write an email to sales@anybodytech.com. Also, there are some upcoming events. From May 16, there will be ICRA 2016, which will be held in Stockholm, Sweden, and this is a flagship conference of IEEE. AnyBody Technology will have our booth there, so if you have any plan to join this conference, then please feel free to visit us there. In July, we will have our booth and free workshop at ESP 2016, which will be held in Lyon, France. So please consider to join this workshop and visit us at our booth as well. Also in September, there will be the musculoskeletal modeling course at Aalborg University, where our academic partner, AnyBody Research Group, is located. Especially this year's topic is focused on the advanced knee modeling. So I hope that many of the audience in this webcast would be also very interested in this nice opportunity. Now we can get started the question and answer session. Here we just have a list of several questions that we have received. So Iwan Jung will try to answer some of the selected questions from those, and I will read some of them. And the first question is, were reaction elements connected to the same point on the distal femur? And if so, where was this point?
The force in each reaction element were calculated for the tibia, and then these forces were applied to the knee joint position in the femur bone.
The next question is, for the superior-inferior reaction elements, could the component pull as well as push, which would not be physically realistic?
The sum of force in the reaction element is equivalent to the sum of the articular contact forces and ligaments and soft tissue forces. Therefore, during the stance phase, compressive force would be dominant in the reaction element, but would pull during the swing phases.
The next question is, how and why was the frontal long leg X-ray helpful for improving the skin marker locations?
It is difficult to determine anatomical location of skin markers relative to underlying bone segment without the aid of skeletal imaging systems such as ultrasound or X-ray. Thus, the marker locations from the static trial alone were not any better than the marker locations from the working trials, as they did not provide the location relative to the underlying anatomy. So long leg X-ray provided clues to estimate marker locations relative to the underlying skeletal system. Yeah.
And there's a very practical question, is how long did it take to develop the patient-specific full body contact force estimation model in AnyBody modeling system for your case?
It took around 10 days to develop and implement reaction elements on the knee. Afterward, it took 1.5 months were spent to develop patient-specific leg models, because it was our first time of trying this method.
And the next question is, what is uniqueness of your method compared to FTK?
The FTK is a hybrid simulation method using both inverse and forward dynamics simulations, but our method uses a pure inverse dynamics simulation so it does not rely on detailed ligaments models or on elastic foundation models. It would be used when kinematics were accurately measured. For example, when kinematics were measured using a biplane fluoroscopy system.
Another question, can we calculate forces acting on lumbar spine the way you have calculated the forces on knee joint? In the knee joint forces analysis, did you replace the ligament to a pressure or force sensor mat?
Yeah, I think this reaction element can replace the reaction force, can estimate the lumbar pressures on the lumbar spine, and we did not replace ligament. We did not use the ligaments, and we did not use the pressure force sensor mat.
Okay, then there is another one. Do you think that this approach could work also in a normal knee? I'm thinking at the role of a menisci, for example, in distributing contact forces between bones. Thanks.
Yeah, we can estimate the normal knee forces during gait or any other daily activities. And yeah, meniscus is really important things to distribute the contact forces, but our study scope is just estimate the medial and lateral force. And yeah.
Okay. Unfortunately, due to the time limitation, now we should stop this question and answer session. I'm sorry if your questions are not addressed now, but all the unanswered questions will be followed up by emails from us afterwards in the upcoming days.